So this is going to be the last lecture, which really focuses on quantifying the inefficiency of equilibria per se. And the point of today's lecture is to change basically two things in the games that we've been looking at so far. The first thing that's going to change is we're going to switch from a domains with negative externalities to domains with positive externalities. So externality, that just means in general, that's sort of the aspect of the social cost or social benefit which an individual is not taking into account. So an individual makes its own decisions according to its own objective function. There's usually some difference between that and what you care about globally, and the externality in effect is that difference. So in the examples we've looked at so far, like routing games, the externalities are negative, right? So when you drive on a road, you don't take into account the fact that you make everyone else's lives worse. In the location games, when you co-locate near somebody, you don't really care about the fact that you take some of their profit away. So from the player's perspective, sort of players near you were a bad thing in the routing and location games. But if you think about it, there's other application domains where there are positive externalities, right? So if you join something like a campus organization or a social network or whatever, hopefully not only do you get benefit, but you enrich other people's experience by being there. Okay, so again, that's something you're not really directly accounting for yourself, but in this case, it's a good thing for everybody else. So I want to talk about a model. It's again going to be a network model, which explicitly has positive externalities, and we'll see what changes. And then the main thing that's going to change, at least in this particular model, is there'll be multiple equilibria. Okay, we're used to that. We've seen examples with multiple equilibria. But here, actually, some of them will be wildly better than others. Okay? And so it's going to motivate wanting to select down and discuss only subsets of the equilibria, which is something we haven't done so far. We've always looked at worst case equilibria. So we'll talk about a couple ways that you could look at particular subsets of equilibria. Okay? So those are the main takeaway points for the day. So the model I want to illustrate these points with is called the network cost-sharing games. So we're still going to have a graph. It could be undirected or directed. The description of the model is the same either way, although technically it seems to behave differently depending on whether it's an undirected network or not. Now, instead of a cost function, that, like we've been having in the routing games, we're just going to have a fixed cost on an edge. So basically, for an edge of this network to be built or to be formed, there is some fixed cost which gets incurred by everybody. So you might think about, building a trench, digging a trench. You might think about, installing, some really fast internet to a neighborhood. There's some fixed cost from which many people benefit. So call it gamma E for this fixed cost. Players' objectives are the same as in the routing games. Each player we're going to assume has a source and a destination, and they're going to want to pick the path that has the smallest cost for that player. Okay. So we're going to say player I needs to connect a source vertex Si and a sink Ti via some path Pi and G, and then given these choices of paths, some subset of this graph gets formed. So namely the edges that are chosen by at least one person. Okay? So network union over I of the paths gets formed. So this is one type of what's called a network formation game, and that's a whole area in its own right. So for example, Professor Matt Jackson often teaches a course on that over in the econ department. A lot of the models, including this one, are pretty ad hoc. It's actually a really hard topic, trying to get sort of good game theoretic models of how networks form, but this is going to be the one that we discuss today. Now, what are the payoffs? So the assumption is, so you pick a path that comprises all of these edges. And just like in routing games, a given edge might also be picked by other people. They might be in other people's paths. There's some fixed cost gamma E that has to be paid jointly by everybody. So we're just going to do the simplest model and assume it's split equally amongst all of the users. Okay, so cost gamma E of an edge that's in at least one path split equally among users. And so hopefully you see what I mean when I was talking about positive externalities, right? If there's some edge and it costs 10, and you're the only one on it, you have to pay the full 10. If you're one of 2 people, then you only have to pay 5. If you're one of 5 people, you only have to pay 2. So here you really want to be joined by your comrades, okay? All right. And then as usual, players pick paths to minimize their cost. And again, the cost, as in routing games, is just the sum over the amount that you pay on each of the various edges. So hypothetically, if we had full control over the system, what would we want? Well, arguably, we'd want everybody to get connected, and we want the overall cost to be as small as possible. Okay? So minimize the total cost of the formed network. So that's the formal description. Let's develop our intuition for the model with some examples. So one thing that can happen in these games with positive externalities is you can have miscoordination problems. So here's an example. I call this the VHS or beta example, which gets more obscure with each passing year. This was even kind of like when I was a kid. So basically, before DVDs, if you can imagine that civilization actually existed then, before DVDs, they were basically just starting to be able to rent movies. Okay, this is like mid-'80s, early '80s, and there were 2 technologies. There's VHS and Betamax, and at least all the nerds said that Betamax was better. That was sort of the consensus among the kind of gearheads. Yet, VHS just sort of got a lead in the market share, and it just kind of took over. Right, because you needed coordination. You wanted the liquor store down the corner to be, you wanted to have whatever, something compatible with the most convenient place to pick these things up. So VHS took over and dominated for a while, till whenever it was, early 90s or something. So how would that play out in a network cost sharing game? Well, imagine that there's K players. So you can think of these 2 links as different technologies that could be chosen. They're sort of, accomplish the same task. They go from the same start node to the same end node, but they have different qualities. In particular, one is way more expensive for society than the other. So imagine all K players just want to connect S and T. And let's look at the pure equilibria. Well, first, let's look at optimal. Right, so what's the optimal solution? No prizes. It's the optimal solution. We want to minimize, right? Yeah, so it's a cost minimization version. Yeah. If it was payoffs, we'd want the bottom. But we want to minimize costs, so we want the top. Okay? So that's all on top. For a cost of 1 plus epsilon. Yeah? So K is the number of players. Epsilon's a positive number. And as usual, I'm labeling the edges with their costs. Now here, the costs, remember, are these gammas. Okay, so these are the fixed costs of an edge. So if anybody uses an edge with some cost gamma E, then the collection of users split that cost equally. So when all K players are on the top edge, they're all paying basically 1 over K. They each pay their fair share of that. And that's a Nash equilibrium, right? A unilateral deviation would multiply your cost by like K squared, so that's not a good idea. But unfortunately, if everybody miscoordinates, and we can get a second Nash equilibrium. Okay, so if all K players choose the bottom link, the fixed cost is K, it splits evenly among K players, so each individual cost share is only 1. And if you deviate unilaterally to the top, and then you're flying solo up there, you play cost 1 plus epsilon. Okay, which you don't want to do. So, this is an extreme stylized example to make the point, but of course, it's not hard to think about examples of this in real life, where people could have coordinated on, option A or option B. One of them's a little bit better, but people coordinated on the one that's a little bit worse. I encourage you to think about real-world examples of that. Okay, so here's a very sort of stark illustration. So another pure strategy Nash equilibrium. Everybody is on the bottom. And so that has cost K. Right? So this is sort of a disaster. Right? This is kind of the simplest kind of example you could think about. And so what we've just proven is that the price of anarchy with these network cost sharing games, remember the price of anarchy is the worst of all of the equilibria, so this can grow as quickly as linear in the number of players, okay? Which is not so good, all right? It's also quite easy to prove that it can't be higher than the number of players. We'll put that on the next exercise set, okay? Now, I don't know about you, but I look at this example and I get a little angry, you know? I kind of feel like, you know, we were trying to model something very sensible. You know, we have this nice Nash equilibrium concept. And somehow, you know, and we have this nice price of anarchy concept, which has guided us well through many applications. And we don't get very, you know, interesting insight into this model. And what's holding us back is this kind of stupid equilibrium that we probably don't believe anybody would really play if there was really such a stark difference between the two outcomes. Okay? So it's sort of not back to the drawing board, but we got to take a step back as modelers and ask, well, if we still believe this is a model worth understanding, and we'd still like to somehow measure the inefficiency of equilibria in some sense, how are we going to do it? Okay, the price of anarchy is not the right concept. Okay, it's too sensitive to pathological worst Nash equilibria. All right, so issue. How to focus only on the reasonable Nash equilibria. Okay. Yeah.
Maybe this is jumping ahead, but don't you just need like 2 people to switch to the top half and all of a sudden?
Yeah, that is a good question. Or that is jumping ahead. So that'll be the back half of the lecture. We'll talk about coalitional deviations. Okay. I mean, one thing to point out is, you know, if I made that a little bit smaller than k, and 2 people switched, then so if I made that k over 2, then 2 people switching wouldn't help. So it doesn't go away as soon as you allow sort of small deviations. But we'll talk about once you allow sort of arbitrarily large coalitions, what happens here. That'll be one of the two. That'll be one of the 2 solutions that we talk about for addressing this point. So just to sort of, you know, so I want to point out, contrast with last week. So last week when we talked about routing and location games, you know, that was sort of a big success, right? Because we had the set of pure Nash equilibria. You know, and we kind of made fun of the pure Nash equilibria as being so small, they might not even exist. You know, and there are all these bigger concepts we care about much more. And, you know, we were just spoiled, right? We could be arbitrarily greedy, it felt like last week. We could just keep making the set bigger and bigger and bigger, and we kept getting these great constant bounds. So the story's a little different in this model, and, you know, other models as well, which is already the set of pure Nash equilibria is sort of too big to reason about inefficiency of equilibria. And we're trying to pick some subset, okay, a so-called refinement of the pure Nash equilibria that we're hoping has 2 properties that are actually pretty hard to satisfy simultaneously, as we'll see. So the first property being plausibility, meaning we can tell some convincing story about why those equilibria are more important than the others, number 1. And 2, that actually we can prove much better worst case bounds on this subset of Nash equilibria than we can on all pure Nash equilibria. Okay? So that would be the dream. We're not really going to fulfill that dream today, but I'll show you kind of the best we can do, the best we know how to do. All right? Good. Okay. So to make sure we understand sort of what we might hope to accomplish, let me show you example number 2, which shows a sort of more robust form of inefficiency that can arise in these network cost sharing games. All right. Example number 2. So that was the VHS or beta example. This is the opting out example. Okay. So all the players are going to have the same destination now, but they're going to have different sources. Okay. K players. Also, unlike the previous example, it's going to be crucial here that the graph is directed. Here, it doesn't really matter if it's undirected or directed. Here, it matters. So, remember, with positive externalities, sharing is good. So the players will have a way to rendezvous. In fact, they'll be able to rendezvous at a personal cost of 0, and then share the remainder of the route to their common destination, t. Okay? Where the joint cost of t is 1 plus epsilon. So if everybody took it, they'd each pay a little bit more than 1 over k. Now, if this was the network, there'd be nothing to do, because everybody only has one strategy. So let me give people an opt-out strategy. Okay? So they can be antisocial if they want, and just go straight to t instead of sharing the ride with everybody else. You can tell your own story about cars and public transit if you want. So what's the cost of opting out? Well, it's going to vary with the individual. So let's say it's cheap for SK to opt out. Okay? It costs 1 over k because they really like their car or they live close to work or whatever. 1 over k minus 1 for the player k minus 1, and so on. Okay? So the cost is 1/3 for the third player, 1/2 for the second player, and 1 for the first player. So let's think about how players make decisions in this game. Actually, first let's start the same way we did before. Let's ask what the optimal solution is. So from a societal perspective, what do you want people to do? Yeah, you want them all to rendezvous, right? Because then all you need to do is pay the 1 plus epsilon from v to t. So opt is 1 plus epsilon. Okay. So is that a Nash equilibrium? Why is it not a Nash equilibrium? Who wants to change? SK wants to change. So when everybody is sharing the VT link, everybody pays slightly more than 1 over k. In particular, player k is paying a little bit more than the cost of its opt-out option. Actually, if you think about it, player k has a dominant strategy to go straight to t. Okay? So given that, given that it's a dominant strategy for SK to go to t, that means that in any Nash equilibrium, it has to be the case that player k is going directly to t. That means in any Nash equilibrium, there can only be at most k minus 1 players rendezvousing at v to go to t. That means in any Nash equilibrium, each of the first k minus 1 players has to be paying at least 1 over k minus 1. But player k minus 1 is unwilling to pay this slightly more than 1 over k minus 1, because it has an opt-out option that's only 1 over k minus 1. Okay? And so that's how the dominoes start falling. Okay? And of course, inductively, this unravels completely. At the only Nash equilibrium, by this process that we did, which is called the iterated removal of dominated strategies, the unique remaining outcome that could potentially be a Nash equilibrium is with all players taking their direct routes from their source to the sink. And that is indeed a Nash equilibrium. Okay. So while the issue in the first example was multiple equilibria, that is not the issue here. Okay? There is only one equilibrium in this example. Okay, so the price of anarchy per se is not what's giving us problems here. It's really more fundamentally about equilibrium and efficiency. So, unique pure strategy Nash equilibria. All players opt out. So the cost is the sum of everybody's opt-out options. So that's just the sum of I equal 1 to k of 1 over I. I'm going to use the notation script h sub k for this, the kth harmonic number. This is essentially the natural log of k plus a constant known as Euler's constant, okay, which is less than 1. Okay. So this is where things stand at the moment in these network cost sharing games. You can have inefficiency, you can have crazy inefficiency, linear inefficiency for intuitively stupid reasons, and you can have logarithmic inefficiency for what feel like more robust fundamental reasons. Yeah?
The cost of all the players put together?
That's right. Okay, so now let's So these are lower bounds in effect, showing that equilibria can be bad in various senses. So let's switch to the upper bound side. Can we say anything positive about equilibria in network cost sharing games? And we can. I'm going to offer you two results. So here's the first one. So this is an old theorem by Anchelevich and many others. So here's the statement, and then we'll sort of talk about what the statement means. So in every such game, doesn't matter what the network is, doesn't matter if it's undirected or directed, doesn't matter what the edge costs are. The claim is, so first of all, there exists a pure strategy Nash equilibrium, right? So that's already a non-trivial statement. Remember, we know models where there are no pure strategy Nash equilibria. So first of all, there always is at least one pure strategy Nash equilibrium. But also, of those, there is one whose cost is not too far from an optimal solution. Okay, so what do we know is not true? We know it's not true that every Nash equilibrium is at all close to an optimal solution. We know it can be off for a factor of k if we wanted a bound that held for every equilibrium. We also know that even for the best equilibrium, right, there's only one equilibrium in the opt-out example. So the best possible approximation ratio we could write right here is h sub k, the lower bound provided by that example. And that's what we're going to get. Okay. So in every network cost sharing game, first, there exists at least one Nash equilibrium. Secondly, one of those equilibrium is a logarithmic factor away from the optimal cost. Okay? And we know that for a statement like this, this cannot be replaced with any smaller number. So there's a name for this. Called the price of stability. And so what this theorem is asserting is that the price of stability in network cost sharing games is at most logarithmic. Now I said when you are trying to restrict yourself to a subset of pure Nash equilibria, what you want are two properties, right? One property is that you get a significant benefit in terms of the worst case upper bound that you can prove, and you do. Right, so in contrast to this linear bound for arbitrary equilibria, we get a logarithmic bound for this best case, if you will, equilibrium. Property two was there should be some convincing story, some narrative that makes it plausible that you care about these equilibria and not others. Okay? And frankly, that story is a little weak with respect to the price of stability. Okay, when you have multiple equilibria, some might be good, some might be bad, and this doesn't really provide an explanation about why this is the one that players will play as opposed to some other one. That said, there are situations where the best equilibrium makes sense, particularly places where, as a designer, you get some opportunity to suggest sort of a norm, sort of the initial play of the game. We touched on this topic when we talked about correlated equilibria last week, this idea of a mediator with this known distribution, where once this trusted third party has picked this distribution, it's stable, no one wants to switch. So similarly, maybe you're designing a piece of software and there are some parameters, that can be free to set by the user. Like for example, how aggressively you decrease your rate once you have network congestion in a network. And you can envision initial default settings of those parameters that you ship the product with as perhaps an equilibrium that you're wanting to initialize people in. Okay? And so then if you're in a position to kind of set the default parameters in some situation, then it makes sense to focus on the best of all of the equilibria. Okay? So you want it to be stable. Subject to that, you want it to be as good as possible in some sense. So those are some of the reasons why people think about the price of stability. But again, I don't want to oversell it. It is a much weaker guarantee than the price of anarchy. Okay. So, for the proof, let me jog your memory about Rosenthal's potential function. which is a key tool in both of the two proofs we're going to do today. The first time you saw Rosenthal's potential function was last week, a week ago. The context then was we were talking about atomic selfish routing games. And we said, well, we're proving these bounds about the price of anarchy, about pure Nash equilibria at that point. And we wanted to know, are these vacuous bounds or not? Do equilibria exist? And I showed you a proof that, in fact, pure equilibria do always exist in atomic selfish routing games. And the proof applies equally well to these network cost sharing games. So let me just remind you the potential function. So Rosenthal's potential function. So the definition, so it's defined on outcomes of the game. Okay, so last week this corresponded to paths in a selfish routing network. Now this is just paths in one of these network cost sharing networks. And how is this defined? You sum over the edges. And on a given edge E, you look at how many people are choosing paths that are using it. So we were using the notation F sub E. And then what you do is you look at the cost function on that edge. I'll explain what this is in our context in a second. So in selfish routing, this was just the usual cost functions. And you evaluate the cost functions with one player, with two players, with three players, and so on, up until the number F sub E of players that are actually using it in your outcome. Okay? So this is exactly what I wrote on the board exactly 1 week ago. Now, I commented at the time that in the proof we used nothing about the cost functions whatsoever. The proof of the existence did not depend on the cost functions being non-decreasing. It could have been anything, same proof would work. So in network cost sharing, games, what is CE of I? How should we interpret this? Remember that in the routing context, this was the per player cost on an edge E when there were I players total using it. So what should this be a function of in the network cost sharing context? Yeah, exactly. Gamma E over I. So in network cost sharing games, this is gamma E over I. So again, let me just remind you that the semantics, this was the per player cost. In a network cost sharing context, the joint cost, gamma, is fixed, independent of how many people use the edge, and it's split equally. So that means the per player cost is just the fixed cost divided by the number of players. Okay? So let me just write this further. Actually, I'm just going to replace this by this. Okay? Everyone okay with that? So in the current context, this is the gamma E is independent of I, so I'll put that over there, and then 1 over I. Okay. So that's just the definition we had instantiated in the current context. So let me remind you what the key property, why is it called a potential function? We proved this last week. The key property is that it, in some sense, simultaneously tracks the incentives faced by all of the players. So if you look at the change in potential, I guess I was using hats. So here, this is where when I deviates from its path in one outcome pi to its path in a new outcome pi hat. So f hat differs from f only in that player I has switched paths from pi to pi hat. So if you look at the change in the potential function value, that's exactly the change in i's cost. Okay? And so what's the change in i's cost? You just look at its old path, you look at its new path. Edges in both don't matter. Edges that are in neither don't matter. The new edges in its new path, well, it pays its new fair share on that, given that it's the FE plus 1th player on it. And then the edges it's abandoned, obviously it no longer pays for that. Okay. So that was the key, that was the one-line proof that we did. Okay. Now, at that time, we used this to prove that Nash equilibria exist, and that proof applies equally well here. The proof is just, among all of the finite many outcomes of this game, look at the one that has the smallest potential function value. Any other outcome only has bigger potential. So any deviation by any player only leads to an outcome with bigger potential. By this defining inequality, that implies that any deviation by any player only leads that player to have higher cost. Okay, and that's the definition of a Nash equilibrium. So the reason a Nash equilibrium, pure equilibrium, has to exist, in particular the global minimizer of phi has to be 1. Okay. So that's sort of the review, and this also establishes this part of Anshel-Levitt's theorem, okay, that there does exist a pure equilibrium. I still have to argue why is there one that's good, okay? But are we okay up to there? The second part will also use the form of the potential function. That's why I wanted to remind you what it looks like. Okay. Good. So proof. So we're going to consider the global minimizer of phi not only to prove that there exists some Nash equilibrium, but actually we will argue this bound for that Nash equilibrium, for the Nash equilibrium which is the global minimizer of phi. That will be the one we single out to prove this better than worst case bound for. Okay? So proof. Let F be the global minimizer. We do F hat. Global minimizer of the Rosenthal potential. We just argued that F hat is a pure Nash equilibrium. And the claim is that this particular pure Nash equilibrium is at most the kth harmonic number times odds. The reasons for this are actually quite elementary. Last week when we talked about the Rosenthal potential function, we talked about how, it's not quite the same as the objective function we actually care about, but it's not too different either. And there's a problem on the exercise set sort of making this more precise. So the Rosenthal potential function corresponded to the area under a staircase, whereas the objective function we cared about was just the bounding box. Right? So I've been trying to develop the intuition through this that, well, obviously the objective function and the potential function aren't generally exactly the same. They're not that different either. So if we have an outcome, which is the global potential function minimizer, if it's inadvertently optimizing this function phi, and if phi, the potential, is a good approximation for the objective we already care about, well then, shouldn't it be that this equilibrium is actually a pretty good approximation of the optimal solution? That is, by exactly optimizing the wrong function, or an almost correct function, shouldn't it be almost correct for the right function? Let's make that precise. So here's the related claim. So what I want to do is I want to compare the potential function to the cost that we actually care about. So let me just remind you what's the cost we care about. Well, so remember, everybody picks their paths, and the union of those paths get formed. So in other words, in the objective function, we pay gamma for an edge, provided at least one person uses it. So it's the sum over the edges, such that Fe is at least 1 of gamma sub e. Okay? So this is our objective function for a given collection of paths. This is the Rosenthal potential function for a collection of paths. So let's just stare at these. Fix an outcome F, and I claim the answers to the questions I'm about to ask don't depend on which outcome f we're talking about. Which of these two numbers is bigger for a fixed f? The yellow number or the pink number? The potential is bigger, right? So both are a sum over the edges. If an edge isn't used by anybody, it doesn't contribute to either one. And basically here, we pick up the first summand of the yellow one, right? We pick up the 1, gamma times 1. Here we pick up a gamma times 1, plus if there's more players, a 1/2, a 1/3, a 1/4, and so on. Okay? So what we just observed was this. So phi can be bigger than the cost. What's the largest factor it could ever imaginably be bigger than the cost by? H sub k. Okay. And this is just true edge by edge. Right, so fix your edge E. This is gamma E times 1. This is gamma E times something, which at its largest is when all the players are using it, and then it's exactly H sub k. So this is the sense in which phi is almost the correct function, and it's exactly what this Nash equilibrium is optimizing. So therefore, it should be near optimal for the real objective. Sorry. Thank you. Thank you. Okay. So just to make sure that's crystal clear, so let's take f hat. F hat is the global minimizer of this potential function, in particular Nash equilibrium. So in particular, a candidate for this bound. Well, by the first inequality, we can bound this above by its potential function value. So as usual, let f star be an optimal solution, one that minimizes the objective function we care about, the cost. By definition of f hat, it has smaller potential than anybody else, in particular smaller than f star. And the potential of f star can be upper bounded by h sub k times its cost. Okay, so that's the proof. So there always exists a Nash equilibrium, a pure Schrödinger Nash equilibrium. The way we prove it is the Rosenthal potential, and then basically as a bonus, the Nash equilibrium we were arguing existed anyways, that already conforms to this h sub k bound. So evidently, and unsurprisingly, in that VHS or beta example, the silly Nash equilibrium with everyone on the K, yeah, it's a Nash equilibrium, but no, it's definitely not the global minimizer of the potential function. The one where everybody's on the 1, that's the global minimizer of the potential function. Question? Because we chose f hat to have minimized phi.
Okay.
So nothing's better than that.
Okay. And f star minimizes the cost.
Yeah.
Okay, cool.
Good. Okay. So that's a canonical application of the price of stability, showing that in network cost sharing games, there always exists something which is within logarithmic of optimal. There's a sort of well-known open question here, which I should tell you about. So again, the reason we know we can't do better than h sub k is because of the opt-out example. Okay? Unique equilibrium, and it's h sub k far from optimal. Now, I'll ask you to think about this on the exercise set. If you make this network undirected, this doesn't work. Okay, this bad example breaks down. It's no longer a bad example if you throw away the directions. And it's actually unknown what's up with the price of stability in undirected networks. Okay? It can only be better than h sub k. And the thinking is at least a little bit better than h sub k, but by how much? And we really don't know a lot about that, despite a lot of effort from a lot of people. There was, the latest progress just appeared in the Fox conference a couple weeks ago in Berkeley, which is one of the top theory conferences. So people are slowly but surely making progress, but that's still really not very well understood. So open. Good. Done with that. All right. Questions? Yeah.
So for undirected in this case, just means that any of the source nodes would go over to Smk and take his.
Exactly.
Okay.
Exactly. So you'd have a killer Nash equilibrium in that network. What does he care? The positive externalities, right? He's like, with the model, he only gets better too, right? He's like, oh, it's 1 over k squared now, not even 1 over k. So, yeah.
So price of stability will be.
Yes, that's right. So I guess I never, yeah. So the formal definition is the best case. So the best pure Nash equilibrium. Now, generally, when people prove bounds on the price of stability, it's hard to get your grubby little hands on the actual best Nash equilibrium. It's an NP-hard problem to compute, for example, generally. So usually you kind of single one out for your proof. And so often you get extra information. So here, for example, we're showing that the global function minimizer is always within h sub k of opt, okay, which is a stronger statement. And it's a strictly stronger statement. So I'll ask you to prove on the problem set, or I think I already did, on the current problem set, that the best Nash equilibrium actually need not be the one that minimizes the potential function. In many cases it is, but in some cases it isn't. Okay? So this really singles out a Nash equilibrium to prove the bound about. Yeah?
Given a potential function, if we could characterize its local minimum, would we get the price of anarchy?
That's right. So when I talked about the potential function, I basically used one direction of an equivalence between potential function minimizers and Nash equilibria. I said, well, if something's a global minimizer of the potential function, then it has to be a Nash equilibria. And we know that the converse of that statement's false, because we know that there are Nash equilibria, which are not global minimizers of phi. However, because we have that condition of potential functions, which says unilateral deviations correspond to changes in the potential, it does say when you have a Nash equilibrium, it does correspond to a locally minimum solution to the potential under the local neighborhood of unilateral deviations by players. So in that sense, there's a bijection between the local minimum of phi and the Nash equilibria of the game.
So I guess that also gives uniqueness to addition of the potential function.
Say it again, I'm sorry?
So that would also give uniqueness, I guess, for the potential function up to, else you could keep some.
Uniqueness of,
So if we know a game has a potential function,
yes.
we would know it's unique, I guess, except for additive.
That's on the problem set. I'm not sure I'm seeing the proof. I know a couple of proofs. We can talk about it afterwards. I'm not seeing, so that's correct. If you think that follows immediately from something I've said here, I'd be curious, actually, because that would be a simpler proof than the ones I know, which would be great. So let's talk afterwards. Okay. All right, so the rest of lecture, I want to talk a little bit about strong Nash equilibria. All right, good. So we're going to look at a different way to restrict ourselves to a subset of the pure Nash equilibria. The goal, again, is exactly the same as before. We want to not have to reason about stupid equilibria, like in the VHS or beta example, and we're hoping we can prove better worst-case bounds. And then there's again going to be the question of, is there a good story for why they're important? Okay. Let's start this way. So, strong Nash equilibria, so Nash equilibria say that nobody can do better by unilateral deviations. That is, you think about k-1 players doing what they're doing, and one player switching. It's also very natural, there was a question earlier in lecture, to think about groups of players deviating in a coordinated way. And I've asked you to think about this notion some on the problem sets. So let me define it for cost minimization games. So strong Nash equilibrium just means that no coalition of players can do better with a coordinated deviation. So, there's a little bit of verbiage here because I have to say there's different notions of what can do better could mean. So a beneficial deviation of a coalition C, or for coalition C, means that nobody should get worse off. So in a cost minimization context, no one's cost should get strictly bigger than before, because otherwise they wouldn't want to be in this coalition. Furthermore, someone should be strictly better off. If everybody changes and if everybody moves and the costs don't change, that's not interesting. We're not worried about that. So a coordinated bid S sub C for a coalition C is such that the cost can only go down for people in C, with everyone outside of C held fixed. So this is for everybody in a coalition with strict inequality for at least one person, for some I in the coalition. So that's a beneficial deviation. Somebody gets better off, nobody gets worse off. And then 2, S is called a strong Nash equilibrium if there's no beneficial deviation for any coalition. Sound good? Yep.
So when a coalition deviates, does it mean can they split up to different places, or do they all have to move from one place to another?
So in the network cost sharing games, what you're not allowed to change is what your strategies are. So all you're allowed to do is change how you're playing the game. So like in network cost sharing, the SI is immutable, the TI is immutable, you're stuck with the SI-TI paths. That said, you can pick any path you want. So in this definition, everybody can pick any path they want for their own SI and TI. Yeah.
The coalitions can say, okay, you take this path, you take this path, or?
Yeah, I mean, it's just for all bid vectors of the coalition. So it's silent on how exactly they would do the coordination. We're not going to worry about that. We're going to say we don't care how they coordinate, because however they coordinate, they're not going to do better. Okay. Good. So this is a refinement of Nash equilibria in the sense that if you are a strong Nash equilibrium, then of course you're also a Nash equilibrium. A Nash equilibrium is exactly saying there's no beneficial deviations for coalitions of size 1. Okay? And again, a good motivation for why you might think to talk about these in network cost sharing games is, as was pointed out, the VHS or beta example. So for the 1 plus epsilon and k, even if 2 players form a coalition, then this will no longer be stable. They'll want to both switch simultaneously to the 1 plus epsilon, where they pay only roughly 1/2 as opposed to the 1 they were paying before. And if in fact, in strong Nash equilibria, you even allow arbitrary sized coalitions, and it's clear that then with an arbitrary sized coalition, everybody's going to want to go to the 1 plus epsilon. And in fact, I'll ask you to prove on the exercise set that in fact, whenever you have a common source and a common destination, strong Nash equilibria are actually optimal. So in other words, the price of anarchy for strong Nash equilibria is 1 if you have a common source and a common sink. Okay? So that's why. So it's clear it's a stronger notion. The story's reasonable. Right? If there really are strong incentives for groups, at least for small groups, say, to deviate, you might expect them to do it. Okay? You really might not expect Nash equilibrium like this to be stable, and coalitional deviations is a reasonable story for why. Okay? All right. So let's turn to what can be proved about them. So this is a slightly newer theorem. So here's how I'll phrase it. So if you have a strategy that's a strong Nash equilibrium of a network cost-sharing game, then the cost of this strong Nash equilibrium is at most h sub k times opt. So there are two differences between the way I stated this theorem and the way I stated the first theorem. In the first theorem, which was about the price of stability, I took care to assert that there exists a pure Nash equilibrium in network cost-sharing games. If you look at this theorem, I'm finagling that point. Okay? I just say if there's a strong Nash equilibrium, then it's near optimal. And indeed, and if there's time, I'll prove this to you, there are network cost-sharing games without strong Nash equilibria. Okay? There are subclasses of them where they are guaranteed, but at the level of generality we're talking about, you might not have any strong Nash equilibria. And that's a major weakness in this result. Okay? So there are instances where it's saying nothing. There are other instances where it's saying something good. The second thing is, in the first theorem, I took care to say that there is one equilibrium that's good. Here, I'm agnostic as to which strong Nash equilibrium you pick. That is, I'm asserting a bound for every single strong Nash equilibrium. Okay? So in the first theorem, we kept our definition of an equilibrium. It was still pure strategy Nash equilibrium. But instead of taking the worst of them, we took the best of them. Here, we're really doing what's called an equilibrium refinement. We're shrinking the set that we're calling equilibria, and we're taking the worst case over this smaller set. Okay, so this is sort of backward from what we did last week, where we kept taking the worst case over bigger and bigger sets. Here, we're sticking with worst case, but looking at a smaller set. So this is called, so I would call, so you hear this called the strong price of anarchy. I would call this the price of anarchy of strong Nash equilibria, restricted to instances where they exist, is at most h sub k. Okay. So that's to compare and contrast this result with the previous one. Before we talk about the proof, let's talk about should we be happy with this result. We already discussed one reason why we might not be, that these things might not exist. But what about just the approximation factor, h sub k, that same h sub k again? Well, that h sub k, if you think about it, we actually need for the exact same reasons that we needed it in Theorem One. So if you think about the opt-out example, what you might hope is that with coalitional deviations, the optimal solution, where everybody rendezvous and jointly pays the 1 plus epsilon, you might hope that that would then be a strong Nash equilibrium. Okay? But no, it's not. And the reason is that actually, remember, SK's incentive to opt out was very strong. This was a dominant strategy. Okay? So, there's nothing some coalition can do for you to make you not play your dominant strategy. Okay? Unless they were able to pay you or something, which is outside our model. All right? So there's not going to be a strong Nash equilibrium in which S sub k goes straight to T. Or sorry, which S sub k rendezvous. Given that there's not going to be a strong Nash equilibrium in which Sk minus 1 participates. Given that there won't be one with Sk minus 2 and so on. So the unique Nash equilibrium in the opt-out example is, in fact, the unique strong Nash equilibrium. Okay? Nothing else is a strong Nash equilibrium. Okay? So this is an example where a strong Nash equilibrium indeed exists, and it is indeed a factor of h sub k away from optimal. Okay? So this is the best we could hope to prove. So let's prove it. So the argument will be, a little bit reminiscent of the price of anarchy analyses we've been studying. But it has a couple of extra clever ideas. Okay. It's not long, though. One clever idea is it actually really, and you're probably not surprised by this given that the answer at the end of the day is h sub k, it will use the potential function in the argument. Okay. And our other arguments about the price of anarchy did not. Okay. The analyses took place in games that had a potential function, but we never talked about it, we never used it in the proof. Okay. It wasn't relevant. All right, so proof. All right. So how did it work with the Nash equilibrium proofs? The first thing we did was like, oh, okay, well, we have this Nash equilibrium. Let's figure out how to use it. And with the Nash equilibrium, we got to say unilateral deviations only make people worse. So that gives us an upper bound on the equilibrium cost. Now here, the hypothesis is stronger. Okay, now we're assuming we start with a strong Nash equilibrium. So the hope is we could get somehow even better upper bounds on people's equilibrium costs. At the end of the day, right, we want to prove something which is not true for general Nash equilibria. So how do we use the fact that it's robust not just under unilateral deviations, but under coalitional deviations? Well, the obvious place to start maybe is, well, somehow the most powerful coalition feels like it's everybody, right? So let's, for any potential deviation by the whole group, somebody becomes worse. Okay. So again, we have this problem, okay, well, what is this hypothetical deviation we're going to apply the equilibrium hypothesis to? But again, let's just do it for the optimal solution. Why doesn't everybody, instead of being in this strong Nash equilibrium, just coordinate and all pick optimal strategies? So since S, so let S star be opt. So since S is a strong Nash equilibrium, what we're going to want to compare is we're going to want an upper bound on the equilibrium payoff of somebody by something else. And what we're used to doing is here we think about a unilateral deviation by I. Now let's think about a coalitional deviation by the full set of players. Okay? So imagine everybody deviates in a coordinated way to the optimal solution. Now in general, when we do that, some people might be better off and some people might be worse off. All the strong Nash equilibrium hypothesis guarantees us is that some player is no better off than before. So there exists a player I such that this holds. Okay? So this is by the Nash equilibrium hypothesis, strong Nash equilibrium hypothesis. Okay. Now to make sure the notation doesn't get out of hand, let's just rename this player I as player K. Okay? So it was the alphabetically last player that is worse off if everybody deviates in a coordinated way. Maybe the other K-1 players get better off. Yeah. Yeah, we're not going to need it though. Yeah. There's also the reason I didn't write strict is because there's this annoying thing where maybe everybody's cost stays exactly the same. That's allowed. So, and this is all we're going to need anyways. Yeah. So say it's the kth player. Okay, so let's actually say K. Now, remember, how the price of anarchy analyses went. We had an upper bound on the equilibrium cost of all K players. And that was important because then we summed them, and then those left-hand sides became the equilibrium cost, which is what we wanted to upper bound. So it's not good enough to just have an upper bound on the equilibrium cost of this one player K. We need it on the other K-1 players as well. Okay? So the question is now, how do we do that? How do we sort of get more upper bounds on equilibrium cost? Well, we've already taken care of K, so let's not worry about it. Let's just be happy with this upper bound on K's equilibrium cost. And let's say, well, since we need an upper bound on the other K-1 players, at the moment we'd be happy with any of them. We're just going to let all of those K-1 players deviate. Again, to what? Again, in our mind, as a thought experiment, we think of those K-1 players deviating to what? Well, to the solutions that we want, the strategies we want them to play in the optimal solution. Okay, and S star. So iterating, And again, renaming players every single time. So I'm going to iteratively apply the strong Nash equilibrium hypothesis, first to a coalition of k players, then to a coalition of k-1 players, the ones I don't have an upper bound on yet, then to the k-2 players I don't have an upper bound on yet, and so on. And I'll get a sequence of k inequalities that look the following. So in the second iteration, there exists some player I, which I'll rename k-1, that would block the first k-1 players deviating to their optimal strategies. Okay. So Ci okay, so remember in the second step, the coalition involves only players k-1 through k-1. Okay, so S sub k, we leave the same in both sides. So this again is a strong Nash equilibrium hypothesis to the first k-1 players. Then we do it again with the remaining players we don't have an upper bound on yet. Sorry, this should be k-1. And so on. Okay. I guess the final one looks like a Nash equilibrium deviation. Okay. And so again, why did we do this? Well, we need an upper bound on the cost of the equilibrium. The sensible way to connect that to the equilibrium hypothesis is to get an upper bound on each player using the equilibrium hypothesis, and this iterated way is how we do it. Okay, so that's sort of clever idea number one. Questions? So now the next thing we want to do is we want to sum, and then the left-hand sides will just become what we care about, equilibrium cost. All right? Now in the price of energy analyses, what we did is we just sort of summed up the right-hand sides. We got this entangled term, and then we had the smoothness arguments to charge it back to other things. Here we're going to do something smarter, actually, which I hope you're sort of breathing a sigh of relief, because if you think about trying to sum these right-hand sides and then directly try to disentangle, it looks a little scary. Okay? So this is the part of the argument where we're going to use the fact that network cost-sharing games have a potential function. Okay? So the use, just jumping ahead a little bit, will be to express these right-hand sides as the difference in the potential at two different outcomes, and then we'll get a nice telescoping sum. Okay? Not unlike what we had for location games, and that'll give us the bound that we want. All right, so pick an arbitrary inequality, and let's notice that we can express one of these right-hand sides as a difference in potential. Actually, let me rewrite this a little bit further. Let's see. Cost of odds. So if I delete those. Good, yes. All right, so here's a question for you. To make these right-hand sides a little bit simpler, let's do the following thought experiment. So the right-hand side here says, what does player k-1 pay? Okay, so what's its sum of its cost shares and all of its edges when the first k-1 players play these paths and the kth player plays some other path? Suppose I deleted player k. Would player k-1, so if this was the initial state of the world, and we're adopting player k-1's perspective, and then I deleted player k. If you're player k-1, are you happy that I just removed player k from the network, or are you sad that I removed player k from the network? You're sad. Because there are positive externalities, right? And people's presence only makes you better off. Remember, your cost share is decreasing with the number of people you share an edge with. Okay? So if I delete these, I guess in some ways this is the way I'm going to elude the entanglement, is if I take these terms, which are a mixed up version of S star and S, and I just delete the parts corresponding to the equilibrium, by only removing players from the system, I only make these upper bounds even bigger upper bounds. I only make the cost shares higher. Okay? So now we're going to apply the potential equality, and then we're going to get a telescoping sum, and then we'll get the bound. Okay? So next, since phi is a potential, oh, I see. Right, good. Let me sum up. So story so far. So we sum up the left-hand sides. We get that the equilibrium cost is bounded above by the sum over the players of the cost share that player I would experience if the entire world consisted only of the first I players and all of them were playing according to their optimal strategies. Okay? That's where we stand. So the claim is that the right-hand side can be equally well written as, let me write it this way. So I claim that the ith summand can be written as the difference between the potential when you have the first I players and they're playing the strategies in Estar versus when you only have the first I minus 1 players and they're playing the strategies in Estar. Okay, whoops, oh, didn't mean to do that. So why is that true? So what's the difference between the value of phi when you take one strategy profile and you just tack on one new player? Okay, that's what that difference is. It just says how much does the potential phi go up if I just throw in this one new player who's playing this path as star I. Okay? Well, this is what the potential is. Okay? And so how much does that go up with one new player? Well, on each edge of that player's path, you're going to pick up one extra summand here. Okay? And if that's the 10th player using that edge, you're going to pick up a gamma e over 10 on that edge. And that's going to be true on every single edge of its path. Okay? What, on the other hand, is the cost of the player I in this outcome? Well, if it's one of 10 players using some edge, its cost share is just the fixed cost gamma divided by 10. Okay? So its cost in that outcome can be written as the difference in the potential value when you delete it or not. So put differently, the cost incurred by a player is precisely the increase in the potential function value that its presence causes. Very much in the spirit of one of the properties of location games. Okay, good. So now we're pretty much home free. So if we just combine these two things, so the cost is at most sum I equal 1 to k So this is a telescoping sum. In some ways, all of these maneuvers have been to get to this point. So what remains when the des Suttles is just the final positive term, which is the potential function value of the optimal solution, minus the last negative term, which is the potential function value of the empty set, also known as 0. Now, we don't really care about the potential function value of the optimal solution as star per se. We care about its cost. But in our proof of the price of stability, what did we use? we use that, yeah, the potential function value might be bigger than the cost of something, but it can't exceed the cost of something by more than an h sub k factor. So using that exact same fact here, this is at most h sub k times the cost of S star. Okay. So that proves that in network cost-sharing games, if you have a strong Nash equilibria, if you have multiple strong Nash equilibria, then all of them are no more than a logarithmic factor more expensive than an optimal solution. And again, the opt-out example shows that no better result is possible. So any questions about that? All right. So I would find this a super satisfying result if it were the case that strong Nash equilibria always existed. Okay? So I think the story for strong Nash equilibria is pretty good. Okay, why do you care about them more than regular Nash equilibria? Well, these are, in a precise sense, a more robust subset of Nash equilibria. And the price of anarchy bound of logarithmic, we've done better. But the opt-out example kind of shows that that ballpark inefficiency seems pretty real in this model. So it doesn't seem like the logarithmic cost doesn't seem like an artifact of how we're measuring equilibrium cost. It seems like something fundamental about the model. So I'm pretty happy with that as well. So the only issue is that strong equilibria need not exist. Again, if you make extra assumptions about the graph, then they can be guaranteed to exist. There's some nice work on that. Maybe I'll say a few minutes about this. I'm not going to go through all the details about why this is true. But I will show you the nature of the example, just because it is an important part of the story. So you only need 2 players to show this. Okay, so we have S1, T1, S2, and T2, and the costs are as shown. So the claim is even this network does not have any strong Nash equilibria. Okay? Now again, it has this potential function, so we certainly know it has some Nash equilibria. That's not the problem. So the issue is just that if every one of its Nash equilibria is not strong, okay, does admit beneficial deviations. So in this network, the claim is actually there's only one Nash equilibrium. So if you drop the strong hypothesis, we know there's one, but actually there's only one. So how do you see that? Well, so here's S1. Okay, it has to get to T1. Okay. So let's think about what's up in the first triangle, right? So one decision that S1 has to make is which way around this triangle does it go. Okay. Now remember, the cost share of a player on one of these edges, either it's going to pay the full cost if the other guy's not there, or it'll pay half the cost if the other guy is there. So the worst case on this edge is going to be 2, right? In fact, this is always going to cost 2. And if there's no reason for 1 to go the other way around the triangle, because then it would pay the full cost of this edge 1, plus it would have to pay half the cost of this edge, which would be 3 halves. So it would pay 5 halves going this way, and only 2 going this way. Okay. So S1 is going to hop straight to this node in any Nash equilibrium. And then, actually, if it has to go to T1, there's only one way around this triangle that works. Okay? So that's where S1 goes. And then the story for S2 is similar. It has to go there, no choice. And then, again, it's going to be, I think I mixed up these labels, actually. No, I didn't. Yeah, that's right. So over here, that's going to be the unique Nash equilibrium. Okay. So unique Nash equilibrium, and then to make sure I finish on time, I'll leave it as an exercise. Again, all that's left to prove is that from this unique Nash equilibrium, you just have to prove that this is not strong. That is, there exists a beneficial deviation. There's some way for these two players to switch strategies in tandem so that one of them doesn't get worse off and the other one gets strictly better off. Okay. So that's a story about strong Nash equilibria. When you've got them, good worst case bounds, they don't always exist. If you're happy with Nash equilibria and you have the luxury of seeding the game with one of them, then again, you can get pretty close to optimal solutions, but there are bad Nash equilibria out there in these games with positive externalities. Next lecture, we'll segue a bit and start talking about dynamics in games. See you then.